everybody. Welcome to my talk, SYCL Beyond OpenCL, the architecture, current state and future direction of hipSYCL. My name is Aksel Alpay. I work for Heidelberg University and I lead the hipSYCL project. If we look at SYCL implementations today, you will find that there are four major SYCL implementations. There is clang SYCL, also known as Intel SYCL, LLVM SYCL or DPC++, which mainly targets devices using OpenCL together with SPIR-V kernels. And recently it has also received an additional CUDA backend, which allows it to target NVIDIA GPUs. Then there's Compute CPP from Codeplay, which uses OpenCL together with SPIR or SPIR-V kernels to target devices. And it also has an experimental backend using OpenCL with PTX kernels to target NVIDIA devices. Then there's SYCL, which in particular can target Xilinx FPGAs using OpenCL. And then there's hipSYCL, which this talk is about, which as the only SYCL implementation does not use OpenCL at all. And it targets AMD GPUs by going directly to rocPRIM, NVIDIA GPUs by going directly to CUDA, as well as any CPU using OpenMP. hipSYCL is an open source SYCL implementation led by Heidelberg University. You can go check it out at its GitHub page. It started in summer 2018 as a hobby project, but it's funded by Heidelberg University since 2019 now. It's not only a toy project or an experiment, it really works, and it's also used by its users for real-world applications on machines of all scales. And I would also like to take this opportunity to thank the community, both users who have provided feedback, but also contributors who have helped to make it better. So let's now talk a bit about the motivation behind the project. So imagine you want to really optimize your code. You want to get the most out of your hardware. In this case, you may want to employ vendor optimized libraries, for example, template libraries like rocPRIM or CUDA. You may want to use the latest hardware features. You may want to use those tensor cores of your NVIDIA GPU, or you may want to use the latest intrinsic. Additionally, for performance tuning and debugging, you may want to use your vendor provided profilers and debuggers. However, not all hardware vendors have adopted SYCL, or at least the building blocks from OpenCL that are necessary to implement SYCL using OpenCL yet. So therefore, we need to find a way to make SYCL resilient against such adoption friction. And the solution to address all these concerns is to implement SYCL directly on top of the programming models that are best supported by vendors. And in hipSYCL, we do this by building on top of hip instead of OpenCL when targeting GPUs. And additionally, there's a CPU backend using OpenMP available as well. As a reminder, AMD hip is an almost zero cost abstraction layer for CUDA and rocPRIM GPUs, which follows the CUDA programming model. And the main difference to CUDA is that it has slightly renamed runtime functions. For example, it's hipmalloc instead of CUDA-malloc, but then if you compile your hip code with an CUDA compiler, then hipmalloc will get mapped back to CUDA-malloc. There are now several solutions available for SYCL in conjunction with CUDA, and they all have different characteristics, so I think it's interesting to compare them to see where hipSYCL fits in. If we imagine a scale from more OpenCL interoperability to more CUDA interoperability, then the solution with the most OpenCL interoperability is the Compute CPP PTX backend. Here you have a SYCL compiler frontend that uses the OpenCL API to submit PTX kernels. And this allows you to work with CUDA hardware. So this really gives you hardware interoperability in the sense that you can run your SYCL kernels on NVIDIA GPUs. The next thing that you can do is you can replace the OpenCL API with the CUDA API. And then you end up with what has been done in the LLVM SYCL CUDA backend. Here you have a SYCL compiler and a SYCL implementation that uses the CUDA API and PTX kernels. And here you get interoperability with CUDA as a software platform. So you can, for example, use CUDA libraries as long as the headers for those libraries do not require a CUDA compiler. And the next thing that you can do is you can also change the compiler, and this is what has been done by hipSYCL. In hipSYCL we have a compiler that understands both CUDA as well as SYCL, even in the same source file. So this means you can really obtain interoperability at source code level. And I think this illustration nicely shows that SYCL is a really flexible solution that can be used to build implementations that cover all possible use cases. Let's now talk a bit more about how hipSYCL works. So a SYCL implementation in general consists of three-ish components. The first component is a compiler component. Strictly speaking, since SYCL is pure C++, you can also implement it as pure library. In this case, you don't need a dedicated compiler component. However, if you want to target some sort of accelerator or compute device, then you need to have some compiler component that identifies kernels, extracts them, compiles them for your accelerator, and maybe also implements some SYCL-specific semantics. Then there's the SYCL interface, which is what most users will probably be most familiar with. These are just the classes and functions that are in the SYCL namespace. So for example, your SYCL queue or your SYCL context or your SYCL math functions. Then there's the SYCL runtime, which takes care of data management, scheduling of tasks, interaction with backends such as OpenCL or CUDA, and so on. And then of course you also need some sort of glue code to tie it all together. The compiler component in hipSYCL consists of clang in conjunction with a custom plugin. So we use the clang, CUDA and hip frontend, but we have a compiler plugin that adds support to the CUDA and hip frontend for SYCL constructs. And this allows us to have a compiler that can compile both SYCL as well as hip and CUDA code even in the same source file. So there's really direct interoperability between CUDA and SYCL code, and you can mix and match as you like. This also means that since we're going through established CUDA and hip tool chains, that you can also expect your kernel performance in hipSYCL to be on par with clang compiled CUDA or hip kernels by design. Additionally, since we have existing compiler toolchains to do the heavy lifting, this allows us to really focus on the SYCL part of the implementation work instead of having to develop an entirely new compiler toolchain. When targeting CPU, as I had mentioned, there's no special compiler needed, and because SYCL is pure C++, so what we have done in hipSYCL, we have implemented SYCL for CPUs as a pure library with some OpenMP parallelization. And to the left you can see the compilation options. So your SYCL code goes into SYCLcc, which is our compiler wrapper, and then depending on which platform you want to target, if you want to target a GPU, then clang will be invoked together with the hipSYCL plugin. Otherwise, your favorite C++ compiler will be used, so clang or GCC or the Intel compiler, whatever you like, to compile your kernels for CPU. When compiling for CPU, there's another library that will be used, which is hipCPU. This is a library we have developed that implements the hip API for CPUs. The Clang plugin at the moment employs exclusively AST transformations. And the most important thing that you need to get to work if you want to get a hip or CUDA compiler to accept SYCL code is you need to make sure that it automatically compiles all code required by kernels for device as well. Because in CUDA you have to explicitly mark functions as device if they're supposed to be compiled for device, But in SYCL this is no longer necessary. The SYCL compiler must be able to figure this out on its own. So our clang plugin must identify kernels, determine call graph inside the kernel, and then make sure that all those functions in the call graph get emitted to device as well. There's an important technical side note, which is that hipSYCL has to parse all kernels initially as host code, because otherwise the clang, CUDA or hip front end will raise an error if you try to call some functions that use CUDA device functions in kernels, because in SYCL they are not marked as device functions. Therefore, from the point of view of clang, before our plugin sees it, it's an illegal. You end up with illegal function calls from host code to device code. So therefore, in hipSYCL, all kernels initially are treated as host code, and then once the hipSYCL plugin takes over, they get turned into device code as necessary. An additional thing that the clang plugin needs to take care of is to implement correct semantics for parallel hierarchical for. For example, the specification requires that variables in workgroup scope should be allocated in local memory. And another thing that we are looking at for the future is to add SYCL-specific diagnostics. Using the hipSYCL compiler component is relatively easy. There's a compiler wrapper called SYCLcc that's written in Python. It's also known as SYCLcc-clang. Both SYCLcc and SYCLcc-clang is the same, so you can use whatever you like. And this just hides all the nasty details, like how to invoke the compiler correctly, how to load the hipSYCL plugin if necessary, how to link against all required libraries, how to set include paths correctly, and so on and so forth. And SYCLcc just behaves like a regular C++ compiler with some additional hipSYCL specific options. For example, you can use the hipSYCL platform argument to set your target platform to CUDA, rocPRIM or CPU, depending on what you want to target. And then if you want to target a GPU, you can also use hipSYCL GPU arch to set your GPU target architecture. For example, SM60 for Pascal or GFX 906 for AMD Vega 20. And all other options that are not hipSYCL specific will just get forwarded to the underlying compiler, clang or something else in the case of CPU. And so you can still use your regular CPU regular C++ compiler flags like optimization flags and so on. On CPU, there's an additional argument for the host compiler that should be used. So with hipSYCL CPU CXX, you can select which compiler you want to use to compile. You can also do these settings with environment variables. In this case, command line arguments will take precedence over environment variables, and if neither is provided, then SYCLcc will just use some default settings that are loaded from a JSON configuration file that's installed when you compile hipSYCL. The SYCL runtime is in principle relatively straightforward, so it implements the SYCL operations on top of hip. However, in SYCL we need dynamic out-of-order processing of tasks, whereas in hip there are only in-order queues. So we need to add this mechanism to hip. And this is done using a signaling mechanism at the moment, using callbacks and hip events. So when an operation is completed, then the SYCL runtime will receive a signal and then will start to submit kernels that now have their dependencies fulfilled and can now execute. And this has some downsides, and I will talk about this later on. The SYCL interface is also relatively straightforward. It just takes functionality provided by hip and the hipSYCL runtime and implements SYCL classes and functions using this. However, invoking kernels requires a bit of trickery. So in principle, to invoke a kernel, the idea is relatively easy. So you have a templated dispatch function that's a regular CUDA or hip kernel with the global attribute. and that accepts the kernel as argument. And then this dispatch function would just create, for example, a SYCL item based on the hip thread indices, and then just invoke the user-provided kernel using this item. And then the parallel for in SYCL could be implemented by just instantiating this dispatch function with the user-provided kernel callable. However, since all code initially is parsed as host code, the user-provided kernel is a host lambda and therefore cannot be invoked directly, because otherwise you would again get an error that you try to call a host function from a device function. So what we do is we add a dummy attribute SYCL kernel, which will only be replaced by a proper global kernel attribute once the initial parsing is complete and the hipSYCL plugin has taken over. So this means that the dispatch function, when initially parsed, looks to clang just like a regular host function. And then in parallel for, we also just call it like a regular host function, except that we also call the hip configure call or CUDA push call configuration to set the kernel launch parameters like the number of work groups and the number of work items. This is necessary because the syntax with the three angular braces to launch kernels is not possible now anymore, because the dispatch function now looks to clang like a regular host function, so we cannot invoke it like a regular CUDA kernel. Now, what is the performance that we achieve with this approach? Let's first look at memory performance using Babel Stream, which is an implementation of Stream for many programming models, in particular SYCL, CUDA, and hip. And in this test, I have done runs using Babel Stream with hipSYCL on a Radeon 7, with hip on a Radeon 7, with CUDA on a Tesla V100, and with hipSYCL on a Tesla V100. And as you can see, the performance is pretty much on par for all tested benchmarks: copy, multiplication, addition, triad, and dot product. hipSYCL sometimes is a little bit slower because of additional overheads, but then on the other hand, it's also slightly faster for some configurations, like for example for the addition on the Radeon 7 compared to hip. So in general, it's on the same level of performance as expected. For compute-bound problems, there are not so many benchmarks available yet for SYCL, as well as other, in comparison to other programming models. One benchmark that is available is a Mandelbrot renderer by Jefferson Mello called ToyProt, which is also implemented for many programming models, and you can get this at Jefferson Mello's GitLab page. And here I've made a run using GTX 1080, using CUDA compiled with Clang 9, CUDA with NVCC, and hipSYCL, as well as Radeon 7 with pure hip compiled with Clang 9, and Radeon 7 compiled with the benchmark compiled with hipSYCL. And you can see on the Radeon 7 you get pretty much exactly the same performance, no matter if we use raw hip or hipSYCL. And on the GTX 1080, hipSYCL is on the level of performance of NVCC, which is interesting in this case because hipSYCL also uses Clang 9 in this configuration. And so probably there's just something in the SYCL formulation of this benchmark that Clang 9 prefers over the CUDA formulation. But in any case, we are on similar levels of performance. I'd mentioned that with hipSYCL you can achieve hip and CUDA interoperability at a source code level. I will now show you how this works in practice. So imagine you want to have an optimized function if you compile for CUDA or rocPRIM, and if you're not compiling for CUDA or rocPRIM, you want to have a regular SYCL implementation to be portable. So in this case, what you would do is you would just check if you're compiling for your target platform. So you can do this with the macros hipSYCL platform CUDA or hipSYCL platform rocPRIM. Then you define your optimized function. What's important is that you mark it as host and device, because all code in hipSYCL is initially passed as host code. Therefore, you need to mark it as host device, not only device. And then you can use the macro SYCL device only to check if you're in the device compilation pass. And if you are in the device compilation pass, you can then call arbitrary CUDA or rocPRIM or device code such as intrinsics and optimized libraries and so on and so forth. And then inside your parallel 4 SYCL kernel, you would then check again if you're just compiling for the target platform. If so, you call the optimized function, otherwise you call your fallback function. To give you a more practical example, let's look at how this would look like if you want to do an optimized group reduction using rocPRIM with hipSYCL. So again, you would define your optimized function. In this case, I call it rocPRIM local reduction. That is defined if we are compiling for rocPRIM. So this is why it's in the ifdef hipSYCL platform rocPRIM. And then if we are in the device compilation pass, we just call the rocPRIM block reduce function and return this value. Then on the right side, in our parallel 4 statement, we again check if we are compiling for rocPRIM. If we are, we call the optimized rocPRIM local reduction function. Otherwise, we have a regular SYCL reduction using local memory, using some scratch local memory. So this is how you would implement a decent reduction in pure SYCL. And this is what you get with this approach. So you can see that especially for the 32-bit data types, 32-bit single precision floating points and 32-bit ints, you get significant speed up by using rocPRIM on a Radeon 7. And this is of course not because pure hipSYCL is slow. I've shown you in the previous test that it achieves performance on a comparable level with pure hip or pure CUDA. But it's just because vendor optimized libraries like rocPRIM can do more optimizations because they can put in more knowledge about the actual target hardware. If you're interested in more hipSYCL benchmarking, then I recommend you also go and watch the talk SYCLbench, a versatile single source benchmark suite for heterogeneous computing, where my collaborators and I present a new benchmark suite and also do some hipSYCL benchmarking. hipSYCL at the moment is still pre-conformance, so there are still features that are not supported, that are specified by the SYCL specification. So the largest of those missing features is images, as well as OpenCL interoperability. Of course, by design, we don't use OpenCL, so therefore we cannot provide OpenCL interoperability, which the current SYCL 1.2.1 spec requires. However, even though there are a couple of bits missing here and there, it's still usable already for real-world applications. Additionally, we still have a static compilation model, so you need to decide at the invocation of SYCLcc which hardware you want to target. So in particular, this implies that it's not yet possible to submit work simultaneously to CPU and GPU, because this would require an additional abstraction layer between hipSYCL and hip. But this is something that we are working on at the moment. And additionally, ndlrange parallel 4 on the CPU backend is extremely slow. And the reason is not really hipSYCL specific. It's because ndlrange parallel 4 cannot be implemented efficiently in pure library SYCL implementations. For example, triSYCL CPU backend is also a pure library SYCL implementation and has exactly the same issue. To the left, you see a simple benchmark that I've done to illustrate this. So this is a simple SYCL triad code running on a CPU with hipSYCL, and you can see that if you use basic parallel 4 or hierarchical parallel 4, you get pretty much the same performance as when using raw OpenMP on the same hardware, but if you use ndlrange parallel 4, performance drops by several orders of magnitude. So this is a massive performance loss. And the reason for this is that ndlrange parallel 4 allows for explicit barriers. So this means that the SYCL implementation needs to be able to guarantee that all work items are able to reach the barrier at some point. And this means that we need to launch as many threads as we have work items in each work group. And this is usually massively inefficient on CPU. Of course, a more efficient pattern would be to have multi-threading across groups and then a loop across the work items. And this is exactly how in hipSYCL basic and hierarchical parallel 4 are working. And as you can see, with this approach, you get the same performance as raw OpenMP. But this approach does not work for ndlrange parallel 4 because we need dedicated compiler support to implement barriers in such a scenario. So you can see some pseudocode below. So if you want to have if you have some barrier in this scenario, we would have some parallelization across the work groups, then a loop across the work items, and then some code, and then a barrier, and then some other code. Then this would be needed to transform into 2 separate loops across the work items in order to implement this barrier. And of course, this requires dedicated compiler support that we don't have by design because we have a pure library implementation on CPU, which has the advantage that we can use any compiler that we want. Finally, I would like to talk a bit about where we are going, what we're currently working on. The main focus of the current development in hipSYCL is an entirely new runtime, which has been pretty much rewritten from scratch. And one of the goals that we want to achieve with this new runtime is we want to have arbitrary backends that are interacting and active simultaneously besides hip, that may have, for example, different execution models. Some backends may be task graph based, other may be based on in-order queues, and so on and so forth. So this would then also remove the restrictions regarding the static compilation model to decide between CPU or GPU, and would also allow us to add additional backends such as TBP or OpenACC, OpenMP5, CUDA graphs, whatever. Additionally, we're also changing the way that a backend queue relates to the SYCL queue. At the moment, we have in our SYCL queue a one-to-one mapping to a hip stream, so an hip in order queue, and this restricts our ability to automatically overlap data transfers and compute. And what we're doing at the moment is we're transitioning to an N-to-M mapping, where N SYCL queues map to M backend queues, where M is determined by the capability of the hardware to run concurrent kernels and to perform concurrent data transfers, such that no matter how many SYCL queues you create, you can always utilize the hardware to the best abilities. We're also adding a very strict separation between the new runtime and the existing SYCL interface. So this means that you can also very easily extract the new runtime and use it for other experiments outside of hipSYCL, for example, and also makes everything much cleaner and easier to maintain. The way that the SYCL interface then works in its communication to the runtime is that the SYCL interface submits operations and can then attach scheduling hints or scheduling instructions to those operations. For example, it could add an instruction that an operation should be executed on a particular device. And this allows us very easily to play with novel scheduling mechanisms. For example, if we don't attach the instruction that it should be executed on a particular device, then the SYCL runtime is free to schedule the operation to any device that it wants, so it can do some automatic distribution of work across devices. We can add additional scheduling instructions for the execution priority, or to add in-order low latency mode and so on. This also allows us, or allows the user in the future to modify scheduling behavior at a sub-queue granularity, because at the moment the only thing you can do is you can construct a new queue with some SYCL properties and modify scheduling behavior using this. But this would really allow the user to also change scheduling behavior for individual operations. Additionally, we're also transitioning the operation submission model to a batch submission model, where the signaling to the SYCL runtime that things have completed only happens once per batch of operations. So this would then help us to get higher task throughput for for large number of small operations, for example. And this new submission mechanism will work roughly something like this. So the SYCL interface submits an operation together with its requirements, for example a kernel with some accessors, and this then gets processed by the DAG builder, which collects these operations and checks if there are any conflicts in the requirements. And if there are conflicts, then it has to order the operations. Then at some point, either when the DAG builder has collected enough operations, or when there's a synchronization point in the code, the DAG builder will flush the tasks that it has collected, which will now be a completed full dependency graph, and will submit this then to the DAG scheduler. And the DAG scheduler then enters an optimization loop, where it plays with assigning execution queues to the operations. If the user hasn't specified, assigning devices for execution to the operations, changing the order of operations and so on, and then gives this to the DAG expander. The DAG expander is responsible for turning all the implicit operations, the implicit requirements that may require some data transfer, for example, into actual operations, or remove them if they are unnecessary. And what comes out of the DAG expander is really only kernels, data transfers, and other directly executable operations. Then this needs to go to the backend executor, which is what will also be used later on to actually execute the kernel, to determine which kind of synchronization operations and where synchronization operations are necessary for this particular backend. And then all of this information goes to the DAG timetable, which will construct some estimate of a cost, potentially by interacting with a hardware model. And this execution cost of the configuration then goes back to the DAG scheduler, which may then optimize further, or may then submit the operations as they are to the backend executors. There could be potentially more backend executors if multiple backends are active at the same time. Alright, so if any of this interests you, then you can get hipSYCL by checking out our package repositories. We provide Debian, RPM, and Arch Linux packages. We not only provide packages for hipSYCL itself, but also for matching LLVM and rocPRIM distributions. We don't provide packages for CUDA for legal reasons, but we do provide installation scripts to install matching CUDA distributions. Additionally, there are community provided packages. There's a spec package for the CPU and CUDA backends. and there are ongoing packaging efforts in the communities of Gentoo, NixOS, and the Arch Linux AUR. And of course, you can also just install it from source by checking out the GitHub repository. Alright, to wrap it up, hipSYCL is an implementation of SYCL for CPUs, NVIDIA GPUs, and AMD GPUs. It builds directly on top of low-level vendor APIs, HIP and CUDA, which gives it full interoperability at source code level, so you can really mix and match with HIP and CUDA. It's mainly targeted at HPC or other use cases that require access to the latest low-level hardware optimizations or vendor-optimized libraries, and allows you to create highly optimized code paths for specific hardware. By design, kernel performance can be expected to be on par with regular HIP or CUDA. And since it's an open source project, I'm always looking for contributors, so if you want to work a bit on it, I'm very happy. And yeah, just check it out on the GitHub page, and if you have any questions, feel free to drop me an email. Thank you.